What you're looking at right now is a quaternion number that defines the orientation of 3D space for this little sailboat. As the quaternion changes, the points in the 3D space are transformed according to its value, rotating the boat about the origin. The quaternion number system is one of those otherworldly things from math that is truly interesting and useful. Using quaternions, we can rotate the ship around an axis by an angle, or change the orientation to a known position, like a bird's eye view of the ship. A quaternion lives in 4 dimensions, and its properties, as well as operations, are what allow for the smooth and precise movement of 3D space. In this video, I show how quaternions are used to describe orientation, as well as rotation, and the elegant method they provide for computing the transformed position of points. I also visualize what's happening in the 4th dimension to answer some questions that can arise when using quaternions. A quaternion is written as some real number plus some real number times I plus some real number times j plus some real number times k. In this expression, the variables w, x, y, and z are real numbers, and I, j, and k are the quaternion units, which have the properties I squared is equal to j squared, is equal to k squared, is equal to I times j times k, which is all equal to -1. The units I, j, and k encode rotation so that the quaternion's operations have geometric meaning. When we multiply 2 quaternion numbers together, the properties of these units are how we know the value of the quaternion produced as a result. Later, we'll investigate the geometric meaning these units encode, but for now, I want to show you conceptually how a quaternion number can define the orientation of 3D space. Let's say we have a quaternion which starts with a value of 1, so it is written as 1 plus 0i plus 0j plus 0k. The 3D space whose orientation the quaternion describes lives in a coordinate system with an x-axis, y-axis, and z-axis. Since we are starting with the value of 1, the 3D space will initially have the same orientation as the coordinate system. One unit in the positive x direction of the space is represented by this green arrow, one unit in the positive y direction of the space is represented by this red arrow, and one unit in the positive z direction of the space is represented by this blue arrow. I'll also draw a cube centered at the origin with a side length of 2 units to help visualize the space. To change the orientation, we multiply the quaternion by another quaternion which represents a rotation around an axis by an angle. For example, let's say we have a rotation quaternion whose axis of rotation is the vector that passes through what we see as the top left corner of the cube, and an angle of 60 degrees in this direction. We write this quaternion as the cosine of theta divided by 2 plus the sine of theta divided by 2 multiplied by the axis of rotation. To perform the rotation, we multiply the orientation by this quaternion from the left, which we'll write as q goes to r times q. I'll also draw a copy of the coordinate system to show how the orientation is rotated. Think of the arrow in this expression as meaning the orientation on the left is transformed to be the orientation on the right, and as the rotation as acting on the orientation. For this rotation, the 2 points of the cube that lie on the axis of rotation will stay in the same place, while the rest of the cube rotates by the angle around the axis, which gives us the orientation of space that looks something like this. To calculate the position of a point that's oriented according to q, we perform quaternion vector multiplication, which you can think of as a function that takes in a point as input and returns its transformed position by multiplying the point by q on the left side and also multiplying by q's inverse on the right side. Given a point's original xyz coordinates, which we write as the quaternion xi plus yj plus zk, this sandwich-like product gives us the transformed position of the point, as described by the quaternion. For example, given this point on the cube as input, the function returns the transformed position of the point. In general, this is how we know the position of the points in space that are oriented by the quaternion. Let me show you what this looks like as an animation. When we apply the rotation to the orientation, the 3D space is rotated around the axis by the angle. For each value between the Quaternion's starting and ending orientation, the positions of the points in space are calculated using the Quaternion vector product. This setup works for any orientation. For example, let's say we have another rotation that describes a quarter of a rotation around the x-axis. We can apply this new rotation to the current orientation by multiplying by the rotation from the left. A quarter of a rotation is pi divided by 2 radians, and half of that is pi divided by 4. So the second rotation is the cosine of pi fourths plus the sine of pi fourths times the axis of rotation, which, since we are rotating around the x-axis, will be 1i plus 0j plus 0k. Now that we are explicitly writing the angle, how do we know which direction this quaternion will rotate the orientation around the axis? The answer is one of the distinguishing features of quaternion numbers. The order in which you multiply two quaternions matters. When we multiply in the order we have here, you use what is called the right-hand rule to figure out the direction the orientation is rotated. If you stick your right thumb out in the direction of the axis of rotation, the direction your fingers curl will be in the positive direction of rotation. In this case, the effect of applying this rotation by multiplying in this order rotates the space a quarter of a rotation around the x-axis in this direction. If you were to apply the rotation by multiplying the orientation from the other side, and also remember to change the order of the Quaternion vector product, the effect would be to rotate in the other direction around the axis of rotation. For now, we'll keep multiplying in the order we have here. Using the right-hand rule, we can write the value for the first rotation, which rotates space 60 degrees in this direction around the axis that passes through the top left corner of the cube. If you stick your right thumb out in the direction of the vector and curl your fingers, the positive direction is this way. Because the angle I've drawn rotates the other direction, its value is negative. A 60-degree angle in radians is pi over 3, so the value is cosine of negative pi over 6 plus sine of negative pi over 6 times the axis of rotation, which is negative 1i minus 1j plus 1k. We also should normalize the axis of rotation to be a unit vector by dividing by its magnitude, which is the square root of 3. That way, every time we apply a rotation, the orientation will maintain a magnitude of 1. Otherwise, we could get some unexpected behavior. Since the magnitude of the other rotation quaternion is already 1, we don't need to do anything. Now that we have the values for two rotations, which act on the orientation according to the right-hand rule, consider what happens if we change the order in which we apply the two rotations. Currently, we rotate around the diagonal axis and then rotate around the x-axis. When we apply the rotations in the reverse order, by rotating around the x-axis and then rotating around the diagonal axis, we get a different orientation of the cube. Since we applied the rotations using multiplication, this is a good example that provides geometric intuition for why changing the order of multiplication can produce a different quaternion as a result. As a mathematician would say, quaternion multiplication is non-commutative. Zooming out for a bit, this setup demonstrates why quaternions are so useful. It shows how to describe the orientation of 3D space using a quaternion, and how to represent and apply rotations using multiplication. But if you're like me, you may have some questions like, why do we divide the angle by 2? And how does the Quaternion vector product work? To answer these questions, we need to unpack what's happening in the fourth dimension. But before we cross that threshold, I want us to take a closer look at Quaternion multiplication and the geometric meaning of the units I, j, and k. The other thing we illustrated with this setup is that the order in which you multiply matters. This is important to keep in mind for the property I times j times k equals -1. Because this property is saying quite a bit more when the order matters than when the order doesn't matter. One way to visualize this is to expand the properties of the units into a table, where a unit on the left multiplies a unit on the right. In the first row, we have 1 times 1 equals 1, 1 times I equals I, 1 times j equals j, and 1 times k equals k. In the first column, we have 1 times 1 equals 1, I times 1 equals I, j times 1 equals j, and k times 1 equals k. In the diagonal, we have I times I is equal to negative 1, j times j is equal to negative 1, and k times k is equal to negative 1. And where things get interesting is the permutations of I, j, and k, which are a more verbose way to express the property I times j times k equals negative 1. You can find each of these products by carefully multiplying both sides of the property and simplifying, but I'll just give them here as I times j is equal to k, where j times I is equal to negative k, and j times k is equal to I, where k times j is equal to negative I, and k times I is equal to j, where I times k is equal to negative j. This is where you can see the non-commutative property of multiplication in action, and why you can get different results depending on the order you multiply quaternions together. When you multiply two quaternions algebraically, by distributing each of the terms across, you need to make sure to preserve the order of the units in the expression to get the correct result. I'll spare you the details, but I like to organize the distributed terms in a table, and after you sum all of the like terms together, we'll get this expression. When we apply a rotation to the orientation using multiplication, this expression is exactly how you can tell a computer to calculate the result of one of these rotations. For our purposes, and so we can calculate the products by hand, let's visualize what it means to rotate the orientation by something like I, j, or k. For example, given how we're writing the value of a rotation, what angle and axis of rotation result in the unit k? Well, if we have an angle of 180 degrees, or pi radians, and an axis of rotation around the z-axis, the value of this rotation quaternion will be cosine of pi over 2 plus sine of pi over 2 times 0i plus 0j plus 1k. Because we divided the angle by 2, the cosine of pi over 2 goes to 0, and the sine of pi over 2 goes to 1, so the value of this rotation is k. When we visualize the orientation of 3D space like this, multiplying the orientation by k has the effect of rotating 180 degrees around the z-axis. Similarly, multiplying the orientation by j has the effect of rotating 180 degrees around the y-axis, and multiplying the orientation by I has the effect of rotating 180 degrees around the x-axis. However, when we applied these three rotations, something strange just happened. The value of the orientation we ended up at is negative 1, which looks exactly like the orientation described by 1. To see what's going on, let's say we start from the standard orientation of 1 and apply the rotation represented by k multiple times. When we rotate by k the first time, we get the orientation of k, since k times 1 is equal to k. When we rotate by k again, we get the orientation negative 1, since k times k is equal to negative 1, which looks exactly like the orientation we started at. Likewise, if we rotate by k again, we get the orientation negative k, which looks exactly like the orientation k. And finally, when we apply k once more, we get back to 1. From how we're writing the rotation quaternion, it'd be fair to assume that rotating by k corresponds to a 90-degree rotation around the z-axis, since pi over 2 is the same thing as 90 degrees. However, a byproduct of visualizing 3D space using the quaternion vector product is that rotations are doubled because we compute the transformed position of a point by multiplying by q twice, once from the left and again from the right by its inverse. This is why the orientations 1 and negative 1 look the same, and why k and negative k look the same. When you visualize 3D space like this, every possible orientation has two quaternions that describe it. In general, if you have an orientation and rotate 360 degrees around any axis, you would get the corresponding quaternion whose coordinates are negated, which describes the same orientation. In practice, this is useful because you can choose the shortest path when rotating between two different orientations. The reason why there are two possible quaternions for every orientation of space, and that multiplying by a unit like k visually corresponds to a 180-degree rotation, and not a 90-degree rotation, lies in the mechanics of the quaternion vector product. This function really operates in 4 dimensions, and to see how it works, let's peek behind the curtain to see what's happening in 4D. If we change the quaternion vector product so that we're only multiplying a point by the quaternion on the left, we can partially visualize what rotations look like in 4 dimensions. I say partially because there's another dimension that is not currently shown. Let's visualize applying the rotation represented by k to the 4D space. Focus on the vectors drawn as the green and red arrows, which correspond to the points I and j. When we rotate the space by applying k, the position where I lands is given by k times I, which is j, and the position where j lands is given by k times j, which is negative I. Now that we've modified the function to no longer multiply by the inverse, multiplying the orientation by k from the left has the effect of rotating the space around the z-axis by 90 degrees. If we were just talking about the points in the xy plane, then this appears to have the effect we want. However, watch what happens to the rest of the points when we rotate by k. The cube appears to get squished in the direction of the axis of rotation. If we follow where the point k goes to, we can see that its position is given by k times k equals -1. Currently, our setup shows this point at the origin, but really it lies in the 4th dimension at a distance of -1 from the origin on another axis. The same goes for other points in the space. Some of their coordinates remain in 3 dimensions, while others disappear into the 4th dimension. Now that we've changed the function, the uncomfortable reality is that 4D space is rotated in 2 directions at once when we apply k. There's the rotation around the z-axis by 90 degrees according to the right-hand rule, and, at the same time, there's another rotation we see as the cube getting squished. The question at hand is, how can we preserve the rotation around the z-axis that we want, while reversing this other rotation so that the cube doesn't get squished? In some sense, I've already spoiled the answer for you. Right multiplying by the inverse of the quaternion does just the trick. But suppose you didn't know that works. It's not clear why you'd consider multiplying by the inverse in the first place. Typically, when you multiply an expression by a number and its inverse, it's like multiplying by 1, so the expression remains unchanged. Something rather clever is going on in the construction of the full quaternion vector product to preserve the rotation around the axis that we want. Let me show you how we can visualize the rotation that we want to reverse by following what happens to the input of 1 to the function. Due to the limitations of our setup, this point appears to be at the origin, but it actually sits at a distance of 1 on the 4th axis. Because we are rotating around the z-axis, we can visualize the 4th dimension by drawing another perspective of the space without the x and y axes. Instead, we'll draw the axis that represents the 4th dimension, where we can see the input sits a distance of 1 from the origin. Technically, this axis is perpendicular to the other 3 axes, which is why it's so hard to draw them all at once, and explains why the number appears to be at the origin of the xyz setup. When we apply the rotation k, the points 1 and k rotate counterclockwise around the origin of this other view of the coordinate system. Let me continue applying k so you can become familiar with the 2 rotations that happen at once. Each time we apply k, space is rotated 90 degrees around the z-axis according to the right-hand rule, and 90 degrees counterclockwise relative to the z-axis and the 4th dimension. Watch what happens if we change our function to visualize space by multiplying the orientation from the right. Now when we apply the rotation represented by k, the space rotates around the z-axis in the opposite direction, but continues to rotate in the same direction as before for the other rotation. At first glance, this doesn't appear to help our cause, since the rotation around the z-axis is reversed, and the other rotation continues in the same direction. However, when you think about it, when we multiply from the right, both rotations now travel in the opposite direction from how we want, and this is where we can use the inverse. Typically, when you think of the inverse of something, there's a sense that the product of the thing and its inverse results in 1. If this is the property we want the inverse of a quaternion to have, we can define the inverse using something called the conjugate. When you multiply a quaternion and its conjugate together, all of the I, j, k units turn into real numbers, and we get w squared plus x squared plus y squared plus z squared. This expression is a real number that is equal to the norm squared of a quaternion, so we can define the inverse as the conjugate divided by the norm squared. We can visualize the inverse as two transformations. When we apply rotation like k, space is rotated like this because we're multiplying by the orientation from the right. Then, if we multiply the points by the quaternion's inverse, this reverses the transformation back to the original orientation. If we visualize space by just multiplying by the quaternion's inverse from the right, space rotates around the z-axis in the same direction as if we are left multiplying by the quaternion, and crucially, in the clockwise direction relative to the fourth dimension. This is just what we need to preserve the rotation we want, while reversing the other. When we multiply by the quaternion from the left, space rotates around the axis of rotation and around this other axis, which we see as a cube getting squished. Then, multiplying by the quaternion's inverse from the right rotates space around the axis of rotation in the same direction again, and reverses the other rotation. If we perform both multiplications at once, space is only rotated around the first axis, but since we're multiplying by the quaternion twice, once by the quaternion and again by its inverse, the angle of rotation is doubled. This is why we divide the angle by 2 when expressing a rotation as a quaternion. So far, we've been visualizing applying the rotation k to the orientation, but this works for any angle and axis. For example, to rotate 120 degrees around the x-axis, we write the rotation as the cosine of pi divided by 3, since half of 120 degrees is pi over 3 in radians, plus the sine of pi divided by 3 times the axis of rotation, which is 1i plus 0j plus 0k. Because we are rotating around one of the x, y, z axes, we can visualize the other rotation by graphing the fourth axis against the axis of rotation. When we apply the rotation and multiply by the quaternion from the left, space rotates 60 degrees around the axis of rotation and 60 degrees counterclockwise in the other view of space. Then, when we multiply by the quaternion's inverse, space rotates 60 degrees around the axis of rotation again and reverses the other rotation. When we perform both multiplications at once, space rotates 120 degrees around the axis of rotation, and the cube stays the same shape. Now that we are rotating around the x-axis, this other view of space is an illustration of something you may recognize, the complex number system. This coordinate system visualizes how a property like I squared equals -1 encodes rotation. The complex number system is worth a lesson in and of itself, but I wanted to call it out by name because quaternions extend complex numbers by adding the units j and k. It's a very interesting question why you can't extend the complex number system by adding just one unit, like j, to represent rotations in 3 dimensions. But alas, that too is out of the scope of this video. This 2D slice of the full space helps visualize how the second rotation is reversed when we rotate around an axis like the x-axis. However, when we rotate around an axis, like the one that points towards the top right corner of the cube, this plane no longer captures the full motion of the other rotation. That said, you can still see the same general principle for how the quaternion vector product works in the xyz setup. When we multiply the points by the quaternion from the left, space rotates around the axis of rotation by 60 degrees, and also rotates in this other direction. Then, multiplying by the quaternion's inverse from the right, space rotates around the axis of rotation by 60 degrees again, and the other rotation is reversed. When we perform both multiplications at once, the cube stays the same shape, and space rotates 120 degrees around the axis. This is how the quaternion vector product visualizes the orientation of 3D space, and why we write the value of the rotation quaternion with the angle divided by 2. It's satisfying to understand how and why the quaternion vector product visualizes 3D space, but it can be equally fulfilling to simply use quaternions to rotate the orientation of something like the sailboat I showed at the beginning. Anytime you want to describe the orientation of an object, such as Earth, consider that quaternions provide an elegant and computationally efficient method for computing the transformed position of points in space. In the next video, I show how to implement quaternions on a computer using the concepts talked about here. We also define the method that quaternions provide to smoothly transition from one orientation to another. If math resources like this add value to your life, it'd mean a lot if you consider joining the Patreon. The link is in the description. I've also added links to a series of excellent videos and interactive articles that show another way to visualize how the quaternion vector product works, made by 3Blue1Brown and Ben Eder.